Something I cover as well is there are other advantages to clear expressions. So without diagrams, the key ideas in a paper aren't necessarily expressed. If I communicate using code, then I actually miss out on expressing certain really key ideas. This is because and this is covered here. So in this section, if I only express the code, I don't actually make any particular claims about architecture design. I make a claim about a specific implementation of a specific thing in a specific instance. So the claim that, for example, this new development leads to improved results isn't really made by the paper, right? Because the paper says this specific implementation serves this specific role. That doesn't allow you to sort of isolate the key factor. And so a diagrammatic expression over a code expression has that additional advantage of allowing scientific claims to be made and scientific claims to be tested, rather than a specific implementation being the key focus. And so why is this needed? What's currently used? What's currently used in the machine learning space are these ad hoc diagrams. Basically, you just show the key details, you connect them together, and there isn't much rigor that goes into it. This is flawed for various reasons. In Attention is All You Need, we can see this diagram over here. However, this diagram is very unclear. It's unclear the axes over which this matrix multiplication happens. It's unclear which axes the softmax occurs over. It's unclear how exactly this operation works. It's unclear where all of these things come from. Lots of things in this diagram are unclear. Things like the changing dimensions of data, which are critical for understanding what this model is doing, how this model is implemented, and why this model works, are completely missed. Therefore, we need an improved diagrammatic method that can express these details and specifically express the changing shape of data and how operations act on that data. This is something which is not covered in the Attention is All You Need paper. And that's not because of any particular flaw, simply the tools required to do this don't exist. The exact expressions, the equations, also fail to express this. This equation, for example, for attention. It is unclear which axis softmax occurs over. The tool to express that doesn't exist here. It's unclear how this concatenation works. It's unclear what the dimensions of all of these are. The tools for that simply don't exist. Linear notation, linear algebra notation, isn't made to express nonlinearities. It's not made to express operations acting over certain axes. However, all these things are really critical to understanding deep learning models. So how do we move on from the sort of current methods of doing things? Here in this section, current approaches and related works, I sort of cover the tools that are currently used, things that come from other domains, and a little bit of the background of what's been done in category theory, which allows for the rigorous study of diagrams. However, these have a certain issue, which is they either express linear operations or they express nonlinearities. Neural circuit diagrams overcome this issue. So let's get into how to read these. And I think a good place to start is with quite intuitive diagrams, where we have our data types. Over here we've got strings, then we have functions as these arrows. In a diagram like this, we can see that f composed with g becomes this operation, right? This is using forward composition, f followed by g, indicated by the semicolon. This is your standard commutative diagram. However, we want to express additional information. We often have tuples. And as soon as we've got tuples, these data types become more complicated. the ways that operations can be combined becomes more complicated. So it's better to express things in a slightly different way. We have lines indicating data types. For example, A, tuple B, tuple C. This would be my memory contains these three variable types. Then we have an operation. This changes the variable types. Then we have another operation and it changes again. So basically the lines represent the types in memory. The boxes represent the functions that act on memory and how they change the types. What we then do is, instead of expressing our tuples like this, we express them like this. We have one line for A, one line for B, and a dashed line between them. The dashed line indicates separation. Tuples are separate, right? Your first and second part of a tuple are independent pieces of data. They're independent types. And so we use the dashed line to separate them. If an operation only acts on B and C, we only show it acting on B and C. It then produces its own output type, which can then be fed to further functions. A diagram like this clearly indicates the inputs and the outputs for every function, or at least their types. It clearly shows which variables are acted on and which are left alone. A diagram like this expresses how operations act on the variables in memory extremely well. In the case of deep learning, our data types are largely going to be tensors. These are things like R3 by 3, representing a 3 by 3 table. These tensors can have higher dimensions, 2 by 4 times 3, etc. We represent these as lines without separation between them. So say I had both this and this in memory, I'd represent it like this. If I saw this column, I would know I've got an R 3 by 3 tensor and an R 2 by 4 by 3 tensor. I've got both of these in memory. If I had a function acting on this one, I could draw it here, or a function acting on these. Tensors are accessed by indexes. Indexes really help formalize the mathematics. And it sort of gets across this idea. If I have a 3 by 3 table, and say this is called array 1, I can access a certain column, say with something like this. This would then extract this column, right? And so you could draw this as a 3 by 3 table, and then an index acting on this one, index 2, and then leaving this one. Of course, if we do this, we start with an R3 by 3 table, and we leave with an R3 vector. We can see it in this diagram. R3 by 3, R3. So indexes are shown in this manner, and they can act on specific axes, and they show how the size of the data changes. This then gets us to a really critical idea when understanding deep learning architectures, which is this idea of broadcasting. A really common instance of this is softmax, for example. If I start with an R 3 by 4 table, tensor, and I take the softmax over this dimension, softmax is an operation on a vector, right? So softmax on its own might be from 4 to 4, something like this, and this indicates softmax. I then do this over each of the 3 columns. So every column has a softmax taken. What is my output dimension? My output dimension is 3 by 4. And this is because softmax is being broadcast over this dimension. And we show it in this manner. So if I've got an operation acting over a particular axis, such as F, I then draw it acting on that axis, and then the additional axes of the table are shown above it. This notation very naturally shows how the other axes shapes are preserved, and it shows the exact axis over which an operation acts. This is broadcasting. Formally, we can define it in the following manner. If I take some index, say 2, then first extracting the second column, so extracting this, then applying softmax to it, is the same as taking this, applying the softmax over every column, getting a new tensor, and then extracting this second column.
Interesting.
And so I can draw this relationship, which defines how broadcasting operates in the following manner. If I have my 3x4 table, I take the softmax over this dimension, and then I extract, say, the second column. That is the same as taking the second column and then applying softmax onto it on its own. So this equivalence defines broadcasting. So this defines broadcasting an operation. So now we've established the tools for a number of things. We've established how to represent data of some particular shape in the following manner. We've shown how to show an operation acting on a specific axis, and we formally defined this in this manner, where there is this mathematical equivalence. So this defines broadcasting, and now we've also got an expression to express a variety of things: the shape of data, the changing shape of data, the way that operations act on specific elements of data. This already gives us so many tools to overcome the shortfalls we see in something like attention is all you need, right? This overcomes many of its shortfalls already. We then get to this other very interesting operation, which I call inner broadcasting. If I've got two tables, 3x4 and 3x2, how do I represent these? 4, 3, then separately, right? These are separate pieces of data. 2, 3. And say I had an operation F. F does the following. It takes a vector of length 4 and it takes a vector of length 3 and a vector of length 2. This is fed through F, and we get, say, a vector of length 5, right? This guy gives 3 different possible inputs, 4 possible inputs for this vector. This gives 3 possible inputs for the second vector. Therefore, we've got 4 times 3 possible ways that we can create the output of F. How do we show this? Well, F is an operation from a vector of length 3 and a vector of length 2, produces a vector of length 5. There are 4 ways to get the first input, and there are 3 ways to get the second input. This is inner broadcasting, and it shows an operation act over the different over-tuple inputs effectively. So now I've got a tool to represent this. A really interesting way that inner broadcasting is frequently used is the case of matrix multiplication. Matrix multiplication, say, between a vector of length 4 and another vector of length 4, sums the individual components. If I've then got 3 different inputs for the first vector and 2 different inputs for the second vector, I can then get 4 by 4, or rather, I can get 3 by 2 different outputs. So I have 3 there and 2 there. How do we show this? Again, let's start with the first input dimension, 3 by 4, and the second input dimension, 4 by 2. These are separate, so we draw a dashed line. Then we have matrix multiplication, which is fundamentally an operation of the following form on a vector of length 4. and then an input dimension of 1. 3 ways for the first one, 2 ways for the second one. This axis of length 1, right? If I've got it, this will be isomorphic to this. This is squeezing or unsqueezing, adding an additional axis of length 1. These are the same, and so I can remove an axis of length 1 at will if it is tensored with any other axis. So now I've got some of our fundamental tools. We've got inner broadcasting. We see how matrix multiplication is an instance of this, and we have more generic broadcasting. These are all the fundamental tools to more clearly express the complexities of a deep learning algorithm. Furthermore, neural circuit diagrams have very natural semantics for linearity. This gets fairly technical, and it's not too critical unless we want to start, analyzing things using these tools, which we won't do in this presentation. But suffice it to say, it's a very powerful way of manipulating things, and it has this very interesting property, which is that if I've got a linear operation f and a linear operation g, and they act in the following way, where I've got one axis and I take f over that axis, which is linear, and I've got another axis and I take g over that axis, which is linear. This is equal to this. So it doesn't matter the order in which I apply it. F can be an average, g can be an average. Averages are linear operations. But I won't be covering that today too much, because for common, the sort of powerful algebraic tools are a very nice consequence of neural circuit diagrams, but for necessarily understanding a specific architecture design, they're not that critical. For developing new ones, however, it can come in very handy. So we have that example, but I would like to cover something else first, which is the particular instance of element-wise operations. If I've got a table, a 3x4 table, and I want to apply an operation to each of these elements, I can show this in the following manner. 3x4 table. What is an element-wise operation? Say I've got my ReLU. ReLU goes from R to the 1 to R to the 1. So this operation is represented like so, 1 to 1. So let's add that here. We know that an axis of length 1 can be introduced and removed freely. So this represents an element-wise operation. It's really that simple. And this is defined using the broadcasting rules, where if I take a particular value, extracted using indexes, and then apply my element-wise operation, that's the same as this expression, applying the element-wise to every component, and then extracting that particular index. As you can see, the rules we've established for neural circuit diagrams, the semantics, very naturally lead to, say, expressing element-wise operations or other things. So these are the basic tools. This is really all it comes down to. And all of a sudden with this, we're able to express operations with a very high degree of detail, and we can avoid the ambiguities present in a typical presentation. So let's now go to some examples. And we'll start with the basic one first. This diagram over here represents a basic neural network for image recognition from a introductory PyTorch example. How does this model work? The inputs to this model are a 28 by 28 grayscale image, right? So I've got my height, I've got my width, And then I've got my channels. There's one channel, it's grayscale. Of course, if I've got something of length 1, I don't need to express that, because R28 by 28 by 1 is the same as R28 by 28. In this example, it's fully connected. So we just take these two dimensions and we flatten them into one axis of size 28 squared. Then we apply a learned linear layer to each pixel. Learned linear layer represented in the following manner. L plus shows there's a bias. So an advantage of neural circuit diagrams is the ability to show these details. Often when you're reading a paper and it's just presented to you, you don't know whether a linear layer has a bias or not. This can actually be fairly important. If you unnecessarily add a bias, it can slow down your training. I can go into this specific instance, but anyway. It's sometimes important to keep in mind because these unnecessary biases can slow down training and make models unnecessarily unstable. So then we have the upper dimension, 512. Here's another advantage. This learned linear layer, I'll have the natural question of, how should I implement this? What code should I use? When I use PyTorch to define a component, such as a learned linear layer, I have to state its input and output dimensions. I know that the input dimension will be 28 squared and the output dimension will be 512. Therefore, we know that the component looks like this. So I don't have to explicitly express that these are the input and output dimensions. I can just read the diagram and see that this is the case. Here as well, we've got our element-wise ReLU. Element-wise ReLU, as we've stated before, can just be written like this. And then I've got my next layer, ReLU 512, L plus. Then I've got my output dimension, 10. I've got my softmax, and this equals my predicted output, y hat. Now let's look on the left. This is exactly what we've implemented. We implement the first linear layer, followed by ReLU, followed by linear layer, followed by a ReLU, linear layer, softmax, output. We can see it here. ReLU, ReLU, linear 512 to 512, linear 512 to 10, softmax, y. Another advantage of neural circuit diagrams is the ability to put things in a box. So I put all of these blue things in a box. My linear ReLU stack, I know, is accessed here. Neural circuit diagrams, by putting components in related boxes, indicate how to implement things. I make every repeated block a module in Torch, and I'm pretty much ready. This diagram not only shows the operation of this model, it shows how to implement it, and how to implement it in an organized, understandable manner. So there's a basic example. Any questions, by the way? Feel free to ask.
Oh, one question from me. So is the basic goal of this paper to like represent any like pseudocode of the paper in like diagram form?
Yeah, you could put it that way. It's pseudocode. Pseudocode often doesn't have strict semantics, if that makes sense. These diagrams are, it's quite exact how to implement them, which is a very nice property. But conceptually, it does have that same idea of let's express what we're doing explicitly and rigorously. So it does achieve that. It does achieve the role of pseudocode, but in a diagrammatic form. Pseudocode also doesn't, for example, consistently say the dimensions of different things. It makes the dimensions of certain things hard to register. And there's other advantages to a diagram, which I'll get to later, to do with computational complexity, which I think is a rather nice consequence of using this method. But thanks for the question. Anyone has any questions?
Yeah.
Please feel free to ask. Yeah. Sweet. Now we can get to the exciting part. Attention mechanisms. Attention is perhaps an extremely important algorithm. It is understanding its specific components is pretty critical, right? And something like attention is all you need doesn't necessarily express that. Neural circuit diagrams, however, have a powerful means to express them. I see some people have joined the voice channel. Do you guys have any questions? Yeah, sweet. So without further ado, let's go into scaled dot product attention. What are the inputs? If we understand the shape of inputs, if we understand how operations change the shape of inputs, we're pretty much already halfway to understanding an algorithm. The input to attention is, we've got queries. Queries have dimension y bar times k. Y bar, so I use the bar to represent when an axis represents the number of something. So typically you'll have a number of vectors of some depth. The depth represents the information per thing. The width represents the number of things. By adding the bar, we can just sort of have a clearer idea of what's happening. We understand the role of the dimensions. So we've got so the queue will be associated to a table of different inputs with some depth k. So this could represent the different tokens in an input sentence. K represents the information we have per token vector. So that's our queue. Our k is similar, but very critically can have a different width to q. Why is this important? Well, it means k can have a different origin than q, which will be very important later on. And again, we've got the dimensionality k. And then we've got v. So what do we do next? We do this. This is transposing, right? I've got a 4x3 table, and I transpose it. It becomes a 3x4 table. What better way to represent it than just lines crossing over and rearranging themselves? So we do a transpose, and then we take a dot product. Matrix multiplication. And we take this element-wise operation. So what this is doing is these k's take a dot product over these k's. This leaves us with a tensor of size. What size is the tensor it gives us? So very, we can just read the diagram. Y bar times x bar. So we've got a dot product is a similarity. So what does this give us? It gives us the similarity between every query vector and every key vector. This is the amount of attention that every query pays to every key. What do we do next? This scaling is just for stability. You've got, as k increases, random variance will increase the scale by square root k. We divide by square root k. Oh, yes. Yeah, so the divide by square root k just gets rid of this excess variance effectively. Then we take a softmax over the x dimension. Why do we do this? Well, we can think. We've got a table that's q bar times x bar. This is the score, the attention score. This is the score that every x pays to every q. And now what we do is we take a softmax over the x dimension. So that'd be over this dimension. A softmax normalizes a score vector to 1. So after the softmax, the sum will be 1, which means that we won't have excess values, right? We know that every one of these y columns, every one of these will be associated to a vector with a net value of 1. It is, in that way, something we can use for a weighted mean. So now that this y bar dimension can give us a weighted mean, we then take the weighted mean over the v dimension, right? And then, of course, this reduces down, and we're left with this. And so our output vector is then, these are just y. Our output vector is y by k. Our output vector is the same size as the query dimension, and we've taken a weighted sum over these values. So we've replaced every query vector with a weighted sum over value vectors, with that weight being determined by the attention score, by the similarity between every Q and every V as determined by the keys. That's attention, and that's the attention mechanism. And this is the attention mechanism explicitly expressed using neural circuit diagrams. This expression, as you can see, is a vast improvement in detail over this one. Everything that's happening has been clearly expressed. The concept behind it has been expressed. The fact that K and V take the same dimensionality is made clear, and the fact that Q can take a different dimensionality is also made clear. This means that K and V can come from a different origin. This is where cross-attention comes in. Cross-attention injects an external sentence or an external set of data into our data. This is how we do multimodality, because there is no reason that y bar or x bar can't be, say, an image. When we do cross-attention, Q could represent a expression in one language, K and V can express something in a different language, meaning we can express the information, the values, from a different language into our original language, allowing for example, translating words. In self-attention, Q, K, and V have the same origin. Self-attention allows a sentence or a set of information to pay attention to itself and to incorporate contextual data, or contextual information rather. When we want to process a sentence, every word in that sentence has meaning that comes from the context in which it is. Attention mechanisms allow us to do this, and neural circuit diagrams allow us to see why and how this is possible.
Question, if you're taking, if I'm not interrupting.
Oh, go for it.
Yeah, so this is exciting stuff. Is it, could you imprint, so you've said there's like an actual literal rigorous semantics behind this, right? So does this mean we could, in principle, use this to validate or verify models, like just from the diagrams?
Theoretically, yes. That requires, these are based on category theory, which gives very explicit semantics. Functional programming, for example, is based on category theory. Category theory gives rigor, it gives reliability, it gives confidence. Every single diagram is an explicit mathematical expression. This thing on the right, it's not just pseudocode. It is a literal mathematical expression, as clear as, say, f of x equals x squared is a clear mathematical expression. The semantics for this, I go into it in my honors thesis, how it relates to category theory, but it means this does give explicit meaning. You could then perhaps make code to verify this. As a one-man team, I haven't exactly got around to this, but theoretically it's possible. You could make a programming language.
Really,
yes.
Yeah, this is really exciting stuff. Do you have the link to your honors thesis somewhere, or?
I do. I can post it in the paper page for the reading group.
That would be amazing. I would definitely be taking a look at that. I'm a big category theory fan, so.
Yeah. No, it's good. So I've just posted it. So that's just on my personal website, pretty much.
Fantastic. I'll be looking at that. Thanks. Sorry for the interruption.
No, thanks for the interest. No, I appreciate the questions. It helps me to sort of gauge where people are.
Sorry, very dumb question. What is category theory?
Oh, yes. So category theory, I'll just give a brief overview. Functions, right? Obey this property. If I take x, I feed it to g. So now I've got g of x. And then I feed it to f. That is the same as, say, composing f with g and then giving it x, right? So it's like, if I've got f is x squared, g equals minus, actually, let's do it the other way around. F of x equals minus x, g equals x squared. Then if I take lambda, negative x squared, which is these two composed, and I apply this to x, I get negative x squared. That is the same as first going x to x squared to minus x. This is the associative property, right? Category theory is just, let's take this and let's study mathematics from this lens. So the associative property, compositionality. Category theory is the study of associative composition. Why is this important? Well, if I develop some diagrammatic scheme, I want to make sure that if I take f of g and then add h, that if I were to isolate this section or isolate this section, I get the same result. That's pretty much necessary for a big diagram to make sense. And category theory offers all of the tools to do this. It then offers these powerful tools for having multiple variables, for having other things, for the particular properties of how linearity, linear functions have interesting compositional properties. This property is quite interesting. Category theory allows us to study this. Category theory is a set of tools to understand and comprehend compositionality. The same way that, say, group theory gives us tools to understand symmetry, category theory gives us tools to understand composition, and to then make things which have reliable compositionality, including, but not limited to, rigorous diagrams. And rigorous diagrams of multiple data types, etc. So category theory, it's a set of tools, really. And it's a set of tools that I believe are particularly useful for understanding deep learning.
Gotcha. Thank you. That makes a lot of sense.
Yeah. Yeah, so there you go. Yeah. We can move on to another very, very exciting algorithm, multi-head attention. We're all familiar with, your standard presentations, which are rather confusing, right? They'll have things splitting and then joining again, but it's not really clear what's happening. With neural circuit diagrams, however, how to implement multi-head attention is made, in my view, rather clear. Instead of having Q simply be R, Y times K, we add an additional dimension, H. So here's the question. How do we add an additional dimension, H? Well, we just add an additional dimension, H. We do this for each of them. So now each of these have this additional H dimension. Great. In multi-head attention, every H index only attends to itself. So if I were to take the ith index of H for Q and the ith index, right, like Qi doesn't interact with Kj unless I and J are equal. Every index only attends to itself. How do we represent this? Well, when I take the dot product, I'm not going to have every I with every j. I'm just going to have I with I. Therefore, the output dimensionality is still just times h. I represent it as so. So this is just the two of them are merged. This expression basically means that if I feed an index I, this is equal to feeding an index I to each. So these two axes always take the same index. When I do this dashed line and I have this dashed line terminate, that is an implicit outer product. An outer product, it's effectively just a multiplication. So what does this mean? This means I take Q, I take K, I multiply them, and I make sure to only ever take the same index for both. These will never take separate indexes. This represents how Q has an additional axis. This represents how Q only interacts with K values that have the same index for this additional axis. So that represents attention heads only attending to similar indexes. Let's move this one here. And then when it comes to V, we do the same thing. When they're brought together, only attend the QK multiplications to V's with the same H index, represented as so. Now, our output is Y, K, H. Then we reduce over these two dimensions with fully connected linear out to K, or out to M, rather. So this is the idea. Over here, we can see this. So this is the more how it looks in implementation. How it looks in implementation is we've got these two values with these dimensions. Over the M axis, we do a learned linear layer. So we preserve Y bar, and we get a K H-shaped data, a K deep vector for each dimension head H. We do that for each one. Then we do the dot product, and we make sure that attention heads only attend to heads with the same dimension. They're being kept separate. Then when we collapse it with V, we do the same thing again. So we've got this KH dimension, then we reduce back out to M. In practice, this allows, say, K to equal 64, so it's 64 deep. H might equal 8. Then our input dimension size will be, say, 512. So we start with a 512 vector, we project it into another 512 vector, and we split it into K and H. We do this for each one, and then we bring it back together. This is multi-head attention, expressed using neural circuit diagrams. So we see how it operates, why it operates the way it does, and we've got very handy notation to do it. What's really exciting about this? Let's skip ahead real quick. So see cell 12, Jupyter Notebook. The Jupyter Notebook is attached at the end. So we will see this here. This is something I think is very exciting about neural circuit diagrams. I've got this, actually I do cover it before, so we're going to go back a little bit. Here. So here I've extracted a section of multi-head attention. Cool. Let's say we conceptually understand this. It's a bit difficult, but the point of neural circuit diagrams is all the information is there. I can sort of bit by bit analyze this and understand what's happening. I basically in a broadcast of the H dimension, but then I make sure the H indexes only attend to each other. How do I implement this? Well, how do we implement standard multi-head attention? You know, that's pretty hard to understand from the attention is all you need paper. But here we can actually sort of see using einsum. Einsum is a really powerful package. If you're not familiar with it, I'd recommend getting onto it. It's really, really useful for expressing linear operations. Why? Especially with neural circuit diagrams. Einsum allows us to, for example, express this. X, K, H goes to K, X, H. This is a transpose of this dimension. X, K, H, K, X, H. There's a one-to-one correspondence. Similarly, with a dot product over here, we start with Y, K, K, X, H, and we go to Y, X, H. Again, that's the Einsum implementation. For diagonalization, it's the same idea. Y, K1, H. K2, so see how there's a comma here? Comma represents the separation. K2, X, H goes to Y, K, K, X, H. The H axis gets reduced. So how do we implement this? Einsum makes it easy. Linear operations, as we saw before, have this interesting property where they can sort of be collapsed. So we can do all of this in one step as simply Y, K, H, X, K, H, Y, K, H, X, K, H, to Y, X, H. That implements it. Because of how the lines are drawn between the input dimensions and the output dimensions, there is a one-to-one correspondence to an Einsum implementation, meaning that not only do neural circuit diagrams indicate how axes interact, they indicate how to implement that interaction, which can often look quite complex.
I'm sorry, that's just cool. That's just very cool stuff. I had to comment.
Yeah, it's a consequence of category theory things. It's really cool. Yeah, so that in general relativity, so Einsum, right? Einstein, he developed this really powerful notation for general relativity expressions, which also deals with linear algebra. One-to-one correspondence with diagrams. It's called Penrose graphical notation if you want to look it up. Yeah, that's another massive advantage of neural circuit diagrams.
I'm sorry,
They're
what was
very
that? What was the
powerful.
name of the notation?
So there's Einstein summation and Penrose graphical. Technically, Feynman diagrams, I'll keep this tangent short, don't worry. Feynman diagrams are an instance of categorical monoidal string diagrams where your intersections, right? Like all this stuff, like all this crazy stuff. These represent linear operations in like the Fourier space, like all of that. Again, this has like that correspondence. This is why category theory is really useful. It unifies all of these ideas, then shows you how to do something really cool like this and be confident in the implementation. Yes, tangent over. Yeah, that's multi-head attention. Displays what's happening, displays how it's implemented. Same with the softmax. In the paper, by the way, if people get around to reading it, this section, Jupyter Notebook, that does all of the implementations of all of these algorithms. Yeah. Then we get to this part, the very exciting, somewhat viral, I guess, diagram for the entirety of attention is all you need. This expresses all the details, the entire algorithm, from the multi-head attention to how we add a norm, bring things together, to the feed-forward layer, the specific element-wise operations. This diagram displays the power and the utility of neural circuit diagrams. This is an exact description of attention is all you need. You could take this and implement the entire algorithm from just this. Neural circuit diagrams as well, they're diagrammatic. We can add descriptions. We don't need to. I don't need to say what this is, but I can. If you want to express your new algorithm or understand an old one, neural circuit diagrams give a really good framework for it. I could remove all of this annotation, and it would still be something I could implement. The annotation just helps. And we'll get to other examples of that pretty soon. Here's convolution. Convolution is these various forms, it's linear, and I go into the details of that. We can show different forms. So convolution, what does it do? We get a x, so here I've got x bar, you've got the bold that represents a vector. This is really x, y. These axes just sort of, they're in tandem, they occur together, they act together, etc. Then we've got our C, our channel dimension. What does convolution do? It splits something which is of this form, XYC, into XY K1, K2C, where we've basically got every one of, what does this give? If I take an X index, so Rx times Y times K, this. If I give an index here, I, and an index here, this will access that same index over here and give me a K1 by K2, which will be like 3 by 3, right? And it'll give me this. So ij here gives me ij plus the surrounding area. And so it has this form. Because I give it I give it j, I go to ij in the original vector, and it gives me sort of local values. I write this convolution tensor like so. And so this would be a 3 by 3 convolution, let's say. Why is this useful? Because if I say do a max, what does this mean? If I do a max, it means I give ij, I then go to the local area around ij of size k1 by k2, and I take the maximum value there. This means we can write a max pool in a 3 by 3 max pooling operation in this manner. I can take a 3 by 3 average pool and show it in this manner, because an average is just an operation, say from R 3 by 3, a local area, and it gives me an R1 value.
Sorry, one question. So at the
Yes.
top, you say like it's like the I and J, and like the kernel is like 3 by 3, but like what's the output of the so is it like that kind of operation, that kernel operation over like the entire image? Is that the output?
Yeah, so this is probably the most convoluted aspect of this. Convolutions are just complex. This is just what they're like. But the idea is, say I've got this location, and this location has an index. So let's take this one. What's my y position? My y position is, say, 5, and my x position is, say, 2, right? This is an image, x bar, c, right? And each one of these then has like c channels here. This doesn't really matter, because we're just going to broadcast over this dimension. And my convolution is going to be this. If I give, so this is the original, this is the convoluted. If I put in indexes 2, 5 into my convolution, I'll get a 3 by 3 matrix, which is just the local values. So this is associated to this, meaning that this convoluted output is going to be x bar, so that dimension is going to be the same. But then I'm going to have this additional k image of size k. So that if I feed this 2, 5, this will come back and give me 2, 5 plus the surrounds.
I see.
And so if I take 1, 1 over here, then this will give me 3, 6, because it'll be 2, 5, this guy, 2, 5, plus 1, 1. And that makes sense, because this, let's say this value, or let's say it goes like this, around. This value, 1, 1, plus 2, 5, will give me this.
Okay, so you're kind of like setting the index at the output, and then you get like a 3x3 kernel, because that's like your kernel size, and then you can select the index. Okay, I see. Thanks.
Exactly. You could view this in a currying manner, where we have, what does this convolution give? What is this convoluted thing? This convoluted thing gives me an index from height, width, to r 3 by 3, right? I give a tuple, which gives a height and a width, and out I get an r 3 by 3 vector. This is what the convoluted image x gives me. We just do some currying, and we see that this is a matrix of this form, because we just chuck that there. This is by far the most technical part of this. And the significant thing, the takeaway, don't worry too much about understanding this exactly, because in practice you can often just skip this. But what it means is we can very clearly see the relationship between max pooling, average pooling, or say a linear convolution where we take each of these 3 by 3s and we add a linear layer. We have an output of size C out, input of size C in. The significant takeaway from this is realizing that convoluting an image is an operation, and an operation which can be inner broadcast in the same manner that any operation can be, meaning we can substitute this with a max pool or a linear layer or an average or anything else. And these are in spirit similar, and this similarity can be clearly seen with neural circuit diagrams. Don't worry too much about understanding that exactly. In practice, we just use 3 by 3 convolutions, and we can just express them with, a component like this, really. But it's an interesting byproduct when you get into the technicalities of using neural circuit diagrams. So let's get to more algorithms. Computer vision, a ResNet. Here we can see, how do I express a ResNet? Your identity ResNet. Well, a ResNet contains repeated blocks. So I draw every single block. I add any additional information needed to understand the block, and I show its input dimensions, its output dimensions. And then I show the blocks. Every block is equal to this thing. Something like stride, by the way, what it does is when I do 2, 5, my 2, 5 index gets multiplied to 4, 10 if my stride equals 2, meaning that if I start with a 300 by 150 input image, say, I access all the values with a 150 by 75 convolution, and I skip every second value, because whatever this index is, I double it and then use that to access the prior one. This is a small example of neural circuit diagrams helping conceptualize convolution in a different, more dynamic way. And so to show stride, I just show S. Whatever my index here is, say it's 2, 3, I multiply it by 2, giving 4, 6, and then I access that value in the original tensor, in the original image. And so I skip values. Therefore, this reduces the size of the dimension by 2, the show stride, or by s, whatever value I use. Anyway, getting to this algorithm, we can see how we've organized the expression, and this really helps for implementation. Let's go there, cell 13 to 15. That should be around here. Block, 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 and the block is equal to this. Let's implement this component first. Well, we've got this norm and activate block, NN sequential, norm, activate. That's how we implement that. Identity resonate is what? Block, block. Well, you know, convolution, convolution, block, 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 norm activate, average pull, flatten, because you know the linearity is taking 2 dimensions, flatten, linear, softmax. This code implements this. Now we define the blocks. Every block is equal to this thing. Norm activate, residual connection, this part, this part, this part, this part, and this part. We do that again, and here we see we've got a repetition, so we just make sure to multiply by n. Lambda starts at 1, goes to n1. Yeah, we have n times this guy. And then I just define what the residual connection does. That's the implementation. Neural circuit diagrams help us organize the code, and they guide implementation, because each of these areas becomes one specific module that we then implement later on. So neural circuit diagrams naturally indicate how to implement an algorithm in an organized, understandable manner. We see the same thing with the unit architecture. We take all the repeated components, we define them separately, and then we utilize them, and we just follow this step by step, with the repeated components being fenced off and being implemented on their own. So there we can see there is a clear relationship between neural circuit diagrams and not just implementations, but often very organized, very understandable implementations. If I want to cross-check this implementation, I just make sure I've done this correctly. Does this align with this? I make sure I've done this correctly. Does this align with this? There's my implementation.
I just noticed you've made one of these for Mixtral, 8x7b.
Yes.
Bill. So yeah, that's it. Yeah, okay. Like the educational value of this stuff is very, like, imagine how easy it would be to keep up with new models if you just had this, like, second page, you have this nice representation, and you can easily keep up to it. Like, it'd be really cool if this was adopted as a standard.
Yeah, I agree. Perhaps biased, but that's a definite advantage. Also, often models make slight improvements on each other, and you can very easily see, right? Like, I can just take my new model, be like, this is the new component I added. And yeah, it allows for that iteration, improvement, development. There's another really exciting thing you can do, which is neural circuit diagrams can accelerate innovation. Typically, slight tangent, when we have a system, we've got some sort of system, and I want to improve it, what I do is I make modifications, and I test each of these modifications, right? I see which work, which don't. I use educated guesses. In order to do this, I need to know the degrees of freedom. I need to know the design space, right? In what ways can I modify this? Which modifications are worth, well, number one, which modifications are possible, which modifications are worth exploring. Neural circuit diagrams really help this because they give a very clear overview of a specific model. Great example. is visual attention. Transformers are great. Can I apply transformers to other models? The answer is yes. But how would I go about doing this? With your typical diagram, this is completely unclear. With neural circuit diagrams, it is made clear. Why? Different modalities are often just different ways that data is organized. In this case, for visual attention, what have I changed? Well, I've just replaced X with X bar. I've replaced Y, which is my query dimension, with Y bar. Now all of a sudden I've got attention that can deal with data of different shapes. I've got attention that can deal with visual information. That's it. It's figured out. In this diagram, instead of having a matrix multiplication over X bar and X bar, instead of having matrix multiplication over X and X, I've got matrix multiplication like this. If I wanted to implement this using INSUM, that's straightforward as well, because I can just read the diagram and do what it says. That's how I go from usual attention to visual attention. That shows the power of neural circuit diagrams in allowing, number one, showing ways to experiment, and then two, showing what the model would look like, and then guiding the implementation. This is a very powerful tool.
Yeah, the visual crutch is definitely seeing small differences visually. That's definitely helpful.
Yeah. It also allows for further experimentation. I can then see what multi-headed visual attention would look like. In this case, right, R3 times 1 is the same as R3. I can add a this one length thing the whole way. It doesn't change the model at all. But as soon as I've added it, I can just wonder, what if I replaced 1 with H? What if I replaced 1 with 8? Now I've got multi-headed visual attention. I could wonder what happens if I change the kernel size from 1 to 3. Here, the convolution, right? If I've got my initial image and I do a convolution, and the size of the convolutions are 1, then it's just basically the original image. All I've done is I've taken R to the power of height times width, and replaced it with R to the power of height times width times 1 times 1. This is what a 1-by-1 convolution does. And I can then see, well, this is basically just the identity. These are the same. So I can freely add this. And then start experimenting. So we can do this innovating method, where we just add like a 1-by-1 axis. We connect them up, we add a 1-by-1 or we add a 1-by-1 convolution, which doesn't change anything, then we experiment. And so here we can see the value of neural circuit diagrams in showing how to deal with multimodalities, how to move from one modality to another. And in this way,
What do you use, by the way, to make these diagrams?
I use this very helpful site, mathchar.io. It's this platform that allows for making diagrams, making mathematical expressions. It's a, what's it called? It's like a see as you go. It's like Word, right? You see the text as you're typing it. It's like that, but for mathematical expressions. Mathchar is very good. I can just start writing and then add R2 by 3. Check it out. Definitely give it a look. Might be to your liking.
Because this sort of made me think of how cool, the dot language or GraphViz language, like there's sort of DSLs domain-specific language is specifically made for like visualizing graphs. But I mean, it wouldn't be like too far-fetched to if we actually have these sort of diagrams to make a DSL that simultaneously has this visual representation, but could serve to validate or verify models or their architecture at least, right? Yeah, just a comment about that. Like,
Yeah, exactly.
Cool stuff.
What I would like to do, because I'm like a one-man team at the moment, as this catches on, there'll be value in someone developing like a drag and drop tool. Like imagine if on the right of the screen, you had like convolution, you had your different things. Over here, we have like a grid. And then I just take my cursor and I just drag things in, and then I connect them up, right? Like you could make a drag and drop interface for designing these. If it's done in this manner, I have all of the information of how things are connected, and then it spits out PyTorch code. If I then do a certain type of fencing, say, so I fence off this area, then the PyTorch code can be organized. This is all possible. Theoretically, this is possible. You can do this. It's just a matter of investing the time to code it, really.
Can you get this from, like, say, theoretically from like TensorBoard and stuff?
TensorBoard, I've had a look at those things. Often with previous mechanisms, like if you do, there's like there is this program and it allows you take an algorithm and it shows you all the back differentiation, right?
Yeah.
Like, yeah, right? Some of you will be familiar with this. I can't recall the name at the moment. The issue with this is this doesn't express the dimensions or the dimensions things act over. So if I do this and I see softmax, I'm like, I've got no idea what's happening,
Okay.
right?
Yeah.
But you could probably take this and then modify to do that. I did a brief experiment with it, and it worked rather well. This is definitely doable.
Oh, awesome. And a final question. So, like, is there anything like in the current deep learning landscape where these diagrams can't work in?
I'm not sure. They mainly express your like tensors and how tensors interact with each other. So if you had like branching and conditionality, I'd imagine you just have to make the infrastructure for that. Every function in a computer code has some input shape, some output shape, right? So you could like do it probably, but I'm not sure for conditional and branching. I haven't looked at it much. Fortunately, however, the deep learning models are really nice because they don't depend on conditionality and branching. Because they depend on tensors and how tensors interact with each other, they're really efficient. Deep learning models tend to scale linearly with depth and like quadratically with the like linear. I mean like the number of layers. You'll get like a linear increase in cost, or you'll get a instead of having a 10 by 10 matrix, I've got a 100 by 100 matrix. I'll get like a quadratic or whatever. It's like polynomial increase. Deep learning models are good because they tend to be based on tensors. The intersection of why deep learning is really effective and the domain in which neural circuit diagrams work is a very close overlap. So what I'm effectively saying is neural circuit diagrams work very well for the most effective algorithms. For branching conditionality, I haven't had much of a look at it. It'd be interesting to see.
Worst case scenario, maybe like recursion instead. Do it the Haskell way, or
Yeah, it'd be possible because ultimately, if I've got a function that has some input x and it returns y, and there's like an if, else, or whatever, at the end of the day, it goes from x to y. I could express this as going from x to y. And all this internal logic is sort of captured here, though it does miss that logic. but I'm not sure of too many algorithms that use branching. So that's rather fortunate. And you could possibly develop it more. It's not something I've looked at particularly much. But branching conditionality is just one case I haven't looked at. I used to think these diagrams wouldn't be good for mixture of experts. Turns out they're actually great for mixture of experts. So you never know.
Interesting. Sorry, one more question. Kind of like after this research, what do you plan to do? Like, do you have like a next step in the neural circuit diagram that you want to do?
Yes. There's two topics I want to look at. Right now, I'm working on a diagram for diffusion. That's coming along well. For SDXL, that's the most complicated algorithm I've looked at. It's multimodal. It's got a UNet. It's got all of these things going on. That's taken quite a while to pass. It'll probably come out in the next few days, and I'll release it like on my Twitter or something. After that, there's two topics I want to look at. Developing the semantics for probability using neural circuit diagrams. This can then consider randomness. It can consider the impacts of quantization. There's all sorts of really cool things that come from this. This is very mathematical. This is where the category theory is really helpful. And I want to further explore looking at computational complexity with neural circuit diagrams, which I briefly do in this paper, but it's something I want to explore further and really formalize and develop.
Gotcha, thank you. Very interesting.
Yeah.
How can we follow you? Do you post a lot on your blog? Do you Twitter and that sort of stuff? Because this is cool stuff. I'd like to be kept up to date about how it's going.
Best ways to go to, I'll post the link to my Twitter. This should do it. Yeah, so you can follow I've got a website, vtabbott.io, and I've got my Twitter at vtabbott_. And there you'll be able to stay up to date. And I'll just post about basically how my research is going.
Cool. Definitely writing that down.
Yeah. So there's one more idea I'll look at, and then I'll be able to end this. Is using neural circuit diagrams for computational complexity. Basically, if I've got this right, this is for like back propagation or forward propagation. Technically, this one. Here I see I've got size 1. Size B times A. So my memory cost is going to be 1 plus B times A. Here I've got an operation, a linear operation that takes an input of A times B. So because it's broadcast over because it's broadcast over A, I do it A times. This is my compute complexity, A times that. So neural circuit diagrams can also be used to analyze computational complexity, which I think is a very neat consequence of using them. But I'll be developing that further. And I think it shows an advantage of this diagrammatic approach over, say, textual pseudocode. But yeah, I think that covers all the key topics I wanted to get through. Yeah, any questions?
Feel free for people to raise hands to get on stage to ask questions if they want.
Yeah, no, go ahead.
Or feel free to type in chat. Yeah.
Yeah.
Personally, I just like to see this. I'm probably like whenever I see a beginner, I'm probably going to link to the appendix of your paper. Is that it's sort of a probably like an excellent way to introduce someone to those particular models, right? Especially the attention, self-attention, the transformer stuff. Pretty good for an introductory course, right?
Yeah. That'd be I think developing a machine learning course based on this would be great, because you don't have to spend half of your time like describing which axis like softmax acts over, right? Like you can really dig in. I'd imagine I'd set up a course that's like, you do 2 weeks, do a bunch of practice exercises for neural circuit diagrams in the first like 2 weeks of the course, and then every week you do like a new algorithm. Like, why not? You don't have to spend time explaining like how they operate. You can explain the concept behind them and everything else. I think that'd be great. Yeah. So there you go.
Thanks a bunch for the presentation. Oh, do you plan to like make like a GitHub repository for this? Cause I think that'd be cool if you can kind of input code and output diagrams or something.
That would be very nice. Developing those tools, I am more on the theoretical end of
Sorry,
things.
I think you cut out.
Oh.
Is it just me? Or?
Oh, can you hear me?
I can.
Okay. I am
Oh,
on
okay,
two
my bad.
computers.
Something's not working on my side of things.
Oh,
Sorry.
all good. But yeah, I'll also be releasing these shirts soon. So it's on my Twitter. If anyone's interested in that. So it's got the whole attention is all you need on the back. Yeah, that's another side project. Yeah, that's so making GitHub repo, I think that'd be great. I think there's lots of code work to do. I like the theoretical stuff. Like I did a minor in physics sort of thing. But as people get interested, that would be awesome. And set up a GitHub repo and you have like, slides and stuff, that'd be great. It'd be great if the community could contribute to that. Yeah.
Awesome, yeah. Yeah, I really enjoyed the presentation and the t-shirts, of course.
Yeah. Yeah.
Yeah, I guess that's all for the presentation questions. So yeah, I guess like for next week, the presentation will be on like merging LLMs and diffusion models. So yeah, stay tuned. And also yeah, thanks for the presentation again.
Yeah. No, it's great. It's a very good community here. Yeah. Thank you for having me on.
Yeah.